Okay, so today we're going to be starting to look at the motion of charged particles in electric fields. Now, this is continuing on from what we just looked at, which was just electric fields. We looked at electric field strength, how to draw electric fields, forces that occur due to electric fields, and so now we'll be looking at the motion of charged particles within. And we'll actually be looking today to begin with looking at electric potential and work, and some equations that go along with that. So as mentioned, the first thing we'll have a look at is work. Okay, so if we move an object over a distance, any object, this case we're talking about some kind of charged object, but if any object is moved over a distance, a force has to be applied. Okay, and that makes sense. If there's no force on something, it's going to remain stationary, or it's not going to move at all. So if we apply a force and we move an object over a distance, we can measure the amount of stuff done to it if we know how much force and the distance it has moved. Okay, we call the amount of stuff work. Okay, so the work done equals the force multiplied by the distance you take that force. Okay, and we'll have a look at an example of that shortly. So work, it's a scalar quantity. And it measures the amount of energy used to move an object. It's also measured in joules. Okay, so there's work done on a charge when it's moving in an electric field, and if we talk about this in terms of energy, it means that the object either gains kinetic energy or it gains potential energy, and the way that works is dependent on which way our object moves. So we have two objects here. Three objects. The middle one is positive charge, and the outer two are also positive charge. So if we have a look at the direction of the top one, two positive charges, they're going to repel, and our object is moving to, the arrow is pointed away, so it's going to repel as well. So as the object moves away, okay, it's going to start gaining some speed, all right, and it's going to gain kinetic energy. Okay, now if this object moves towards, that's not natural. Positives coming together is not natural, so it's going to gain potential energy. It has the potential, a higher potential to move away if we bring these things closer together. All right, so if we what we gather from that is if we place a charge in an electric field, it will have an energy due to its position in the field. Okay. Now, if we move the charge in the electric field and there's a change in energy, there has been work done. Okay, so work occurs when there is this change in energy, and that's really important. Okay, what would this amount of potential energy gained depend upon? We'll have a look at that now. So we're going to introduce a new term now, and we have learned already that the energy of a charged particle depends on the work done to the particle. Okay, and it also depends on the size of the charge on the particle. So what we can do is if we divide those two and normalize it, we get this term called the potential difference. And that is indicated here. So the potential difference is represented by this delta V term. Okay. The potential difference is the work done divided by the charge in question. Okay. Now the potential difference is measured in joules per coulomb. The reason for that is this equation. Work is in joules, charge is in coulombs, which is in joules per coulomb. Now this is much like momentum in that we don't really use joules per coulomb to measure potential difference. We use the term voltage, and you would have heard that before. That is a capital V for voltage. Okay, now again from that equation, work done, sometimes it's represented by this delta E, the change in energy. We're going to just leave it as a W. The unit for that is joules, and 1 volt, so 1 volt delta V is defined as the work done per unit charge. So let's have a look at an example of this. the question is how much work is done. So the first thing we know is we're being asked about work. How much work is done moving an electron across a potential difference of 100 volts. So we know we want to work out the work done, and the potential difference equals 100 volts. Okay, and from our previous slide, we know we have the equation voltage equals the work done divided by the charge. Okay, so we also need to know the charge, and from our equation sheet, we know the charge of an electron is 1.6 by 10 to the negative 19. Okay, so we want to know the work done, so we have to rearrange this equation. The way we do that is times both sides by Q. That will cancel this. Times that by Q. We're left with Q delta V equals W, the work done. Now we just put those numbers in, 1.6 times by 10 to the negative 19 times by 100. All right, that's equal to the work done. And you should put that in your calculator, or you can multiply these tens. You get 1.6 by 10 to the negative 17 is work, and I just sum that up in one equation. So the work done equals 1.6 by 10 to the negative 17, and the work done is measured in joules. So put that in. Okay. So sometimes some of these terms are a little bit wordy. However, once you get your head around the equation and what it's asking for, they are fairly straightforward so far. Okay, so we're going to introduce the term now electron volts. And electron volts are really important because we're dealing with charges like electrons, which are really small, times 10 to the negative 19. We need a term that we can get a more appropriate number to look at. Okay, so 1 electron volt is the work done. So first of all, electron volts measured work done when the charge of 1 electron moves through a potential difference of 1 volt. Okay, so if we move 1 electron across 1 volt, that is 1 electron volt. And we'll have a look at an example of this in a moment, but 1 electron volt equals 1.6 by 10 to the negative 19 joules. So that's the conversion. So when we're dealing with these numbers, when we're calculating work done, we always have to use joules, okay? And then we can convert our final answer into electron volts. So if we want to go from electron volts into joules, we have to multiply by 1.6 times by 10 to the negative 19. And if we want to go from joules back to electron volts, we do the opposite. We divide by 1.6 by 10 to the negative 19. Okay. Now, in the definition, the work done. Okay, we have an equation for that. We have work done equals Q delta V. Okay, so the work done when 1 electron has a charge of 1.6 by 10 to the negative 19 across 1 volt times by 1. All right, anything times by 1 is just the original number. So that equals 1 by 10 to the negative 19 joules. Okay. Now, if we want to, we're in joules, we always calculate the number in joules. If we want to convert it to electron volts, we divide by, so our answer was 1.6 by 10 to the negative 19. We have to divide by 1.6 by 10 to the negative 19, which equals 1, okay, and the unit becomes electron volts. So that's where that term comes from. We never do any calculations in electron volts. You always convert to joules first, and you can convert back to electron volts afterwards, but we'll have a look at that now. So another example, in an X-ray tube, electrons are accelerated across a potential difference of 30,000 volts. So we already know delta V equals 30,000 volts. Okay. We also know that it's an electron. So the charge of an electron is 1.6 by 10 to the negative 19. All right. And we've been asked to work out the energy gain, so the change in energy, which is W. So we don't know that, but we do know the equation for it is Q times delta V. So Q is 1.6 by 10 to the negative 19 times by 30,000. Okay. Now we put that into our calculator, and that equals 4.8 by 10 to the negative 15 joules. All right. The question's asked us to find it in electron volts. So the way we go from joules to electron volts is we divide by the charge on one electron. So we need to divide this number. So this is the work in joules, but if we divide it by 1.6 by 10 to the negative 19, okay, we get, put this into your calculator again, you get 30,000 electron volts. All right. So we can never use electron volts in an equation. I'll just reiterate that again. It's really important to understand. But we do give our answers a lot of the time in electron volts, and you'll be asked to do that. So the second part asks, what is their final kinetic energy? Okay, so the work done measures the change in energy from the start to the finish. Okay, so, and in the question it says electrons are accelerated, and that we kind of presume that they're starting at 0 kinetic energy, and their exchange is 30,000 electron volts, or 4.8 by 10 to the 15 joules. So those are the same. So I'll just write kinetic energy final. It equals 4.8 by 10 to the negative 15, or 30,000 electron volts. And this answer would be in joules, obviously. Okay, so a few interesting definitions there, but I think the mathematics is fairly straightforward.